Vanderbilt test method 678 is designed for measuring the viscosity of the thixotropic dispersions of our natural smectite clay products. VGAM, magnesium aluminum silicate. Vanatural, bentonite clay. And Van Gel, magnesium aluminum silicate. This test method is the viscosity procedure found in the magnesium aluminum silicate NF monograph. This procedure is a vital quality control method. It is an identification method for various types of magnesium aluminum silicate as described in the NF monograph. Following the procedure exactly as written is necessary so multiple labs can reproduce the results. Deviating from the procedure may produce results outside of specifications. Because of the rheological properties of these clays, strict adherence to test method, sample size, water quality, energy input and timing are required. A 500-gram test dispersion. Purified or distilled water with specific resistance of at least 200,000 ohms. Wearing blender shear at 14,000 to 15,000 rpm, with shear-induced heating to greater than 30 degrees Celsius. Exactly 3 minutes of shear, 5 minutes of viscosity development, and 6 minutes at 60 rpm for viscosity measurement. This table shows the specification range, specification testing concentration and viscometer spindle for each product. This information was collected from the specification sheet for each grade. The last column lists the spindle for the LV or equivalent Brookfield viscometer operating at 60 rpm. If the viscometer scale reading is less than 10% or greater than 90% of full scale, repeat the entire test using the next lower or the next higher spindle. To demonstrate the test method, we will use VGAMR, which requires a 5% dispersion. That is, 25 grams of clay in a 500-gram dispersion. This requires that we account for the moisture content of the clay. Using a tiered petri dish or watch glass, weigh a minimum of 10 grams of sample. Note the sample weight. Dry in a 100 to 110 degrees Celsius oven for at least 2 hours, or to a constant weight. Cool the dried sample under dry, desiccant conditions that prevent moisture reabsorption, and then weigh. Calculate the moisture content, as shown, and then the amount of water needed for a 500-gram dispersion. Add 473.23 grams of purified water at 25 plus or minus 2 degrees into the 1-liter Waring blender jar. Put the cover on the jar. Connect the blender to the rheostat. With the rheostat in the off position, set the blender speed on high. Remove the clear plastic insert in the cover. Using the rheostat for speed control, turn the blender on at a low speed creating a vortex. Slowly add the 26.77 grams of VGAMR to the water. Replace the plastic insert. Adjust the blender speed to 14,000 to 15,000 rpm and blend for 3 minutes. During the first minute, scrape any particles adhering to the walls of the jar into the dispersion. At 3 minutes, stop the blender and pour the completed dispersion into a 600 ml beaker or 16-ounce jar. The dispersion temperature should be 33 plus or minus 3 degrees Celsius. Allow to stand for 4 minutes. Lower the spindle into the dispersion and let it stand 1 additional minute. Total standing time is 5 minutes. Run the viscometer at 60 rpm for 6 minutes with the number 2 spindle. Record the scale reading at 6 minutes. When these steps were followed for this demonstration, the result was 235 centipoise. Consistently controlling every step of the test method is the key to obtaining correct and reproducible results. Controlling water purity is necessary for limiting the impact of electrolyte on dispersion viscosity. Controlling the mixer speed is necessary because dispersion viscosity is affected by the amount of shear. Controlling the water temperature is necessary because dispersion viscosity is strongly affected by temperature. Both the initial water temperature and the heat input from the high shear mixer. Because the clay dispersion is thixotropic, viscosity increases quickly after it is poured into the beaker or jar. That is why a fixed interval, 5 minutes, is stipulated before the viscometer is started. After the viscometer is started, the dispersion continues to thicken, but the shear from the rotating spindle counters formation of the clay structure. By 6 minutes, the building of clay structure and the disruption of that structure by the spindle have reached equilibrium. This provides a steady viscosity reading. Following the procedure as written is necessary for reproducible results. Next are several examples of the effect of varying the procedure. Curve B illustrates how lower mixing speed and shorter mixing time provides less shear and less shear-induced heating. The result is much lower viscosity. Curve C shows the result from maintaining the prescribed energy input, mixer speed, time and heat input, but not allowing any time for viscosity development, or for equilibration of thixotropic structure building and the spindle's disruption of that structure. Curve D shows the result from maintaining the prescribed energy input, mixer speed, time and heat input, but allowing only a shortened time for viscosity development and too short a time for equilibration of thixotropic structure building and the spindle's disruption of that structure. Proper control of all test method requirements, and consistency in their execution, is the key to proper and reproducible results. Purified or distilled water with specific resistance of at least 200,000 ohms. Wearing blender shear at 14,000 to 15,000 rpm, with shear-induced heating to greater than 30 degrees Celsius. Exactly 3 minutes of shear, 5 minutes of viscosity development, and 6 minutes at 60 rpm for viscosity measurement.